Hello everyone, welcome to ECE410 Power Electronics. This is the first class, introductory class. So my goal for the summer is to provide you video lectures. So before you come to the class, you should review the lectures. And in the class, we're gonna spend most of our time to solve the problem. So you have the theoretical background through the video lectures. When you come to the class, we're going to apply this theoretical background to solve problems so you will get the best out of the class. That's my goal. So your job is to watch the video before you come to the class and take necessary notes from the video. So first class is just introduction. So we're going to introduce the power electronics to you in this lecture. So power electronics and the society. If you look around you, there is no application around you that does not use some kind of power conversion. For example, if you look at the list over here, motor needs some kind of power conversion to control the speed. Then your electric vehicles is full of power electronics inside it because it needs all kinds of power conditioning. And any thing you buy from a store, inside that there should be a electronic circuit, and that's basically a power conversion circuit. Then what is there is this basically SCR, silicon control rectifier, IGBT, and other power electronic devices like your. We're going to learn about it when I go through that course. So one of the very common use nowadays is your wind turbine. If you look at the inside the wind turbine, you will see this picture over here. So what is this? You have a blade, your wind coming in, right? Then you have your mechanical adjustment. Then you have gear system and your generator right here. So generator will produce electricity. That electricity coming out of the generator, it depends on the wind speed. So that generator will produce the electricity that is variable frequency and variable voltage. So your voltage could vary from zero for this particular application 0 to 690 volt, and your frequency can go from anywhere 10 to 60 hertz. But when you use electricity, you want a fixed voltage, you want a fixed frequency. For us, for a household application, we want 120 volt, 60 hertz, right? So we need that. So how do you get it? Then from here, you need to go through some conversion to do that. First is power electronics converter over here. What it does, it will take this variable frequency and variable voltage, will make it a fixed voltage over here and fixed frequency. So what goes inside the black box, think about it, how you can do that, what goes inside the black box. And after you have that, you have transformer to step it up, and ultimately will make it 161 kV for this particular application to connect to the grid. So grid system over here is 161 kV, all right? So, so that is a particular example of your wind turbine, and that's like hundreds of examples around you about the power this application. So if you look at here, the wind turbine, we just talked about that electric car right here. You know that inside the electric car there's a lot of conversion circuit, and if you want to connect your solar or photovoltaic system to anything you in your household, you need a converter and motor controller right here. And also your heating and cooling system now is controlled by the power electronics device also. And also your LED over here, this LED, this guy is basically a power electronics converter. Your LED cannot work with 120 volt AC. The LED needs a particular DC voltage. So when you get the 120 volts here, you have to have a conversion circuit behind it to convert it to the voltage that your LED needs. And so that's what is LED has. If you ever break LED light bulb when is fused, you can see that there's a power electronics circuit behind these LED bulbs, all right? So power electronics circuit almost everywhere you can think about it. So what is the challenge for us for the future? Biggest challenge for us is energy storage. The biggest challenge, I would say, is energy storage. Let me fix this one. Is still energy storage. So you know that your capacitor is an energy storage device, right? So let's say that you have a capacitor cap over here. is voltage is 375 volts, and your capacity is 2700 microfarad, right? So then how much energy is going to store is half C V square. You all know that equation. If we use that equation, you will see that your energy over here 190 joules if we apply this equation, right? So joule is watt times seconds. So your joule is watt times second, right? So then so if you have a let's say you have a 20-watt light bulb, you have a 20-watt light bulb, how much this one can supply that 20-watt light bulb? So you have 190 joule here, right? You have 20-watt light bulbs and seconds. So if you look at the second now, you will see that 190 over 20 will get 9.5 second, right? So for this calculation, this capacitor can only supply 9.5 seconds of energy to a 20-watt light bulbs. This is not practical at all. This is not practical at all. But if you look at the battery, battery also has limited capacity. But look at the battery. If you have battery, let's do it over here. If you have a battery of, let's say, 48 volts, right, and 6 power with the 6 so if you have a 48 volts battery, so what is the capacity you need? What is the amp hour capacity to supply a 1 megawatt load for 6 hours? How to do that? So capacity is your energy. You all know that energy is power times time. So power times time is energy, right? So I have power here is 1 megawatt, so 10 to the first 6, right? Watt. Then I have 6 hours, right? So that's my energy, right? So then I have the battery capacity is amp hour. How do you get the amp hour? Amp hour should be energy is a watt hour, right? So watt hour, so it's watt hour here. So 10 to the first 6 times 6 watt hour divided by voltage, which is 48 volts I have, that will give you amp hour. So watt hour divided by voltage will get the amp hour. And that if you do the math over here, you'll see that that would be 125,000 amp hour. So now you need battery capacity of 125,000 amp hour. Is this practical? You need too many batteries. You need too many batteries to connect in series and parallel to get to this. So that's why energy storage is the biggest challenge for the future if we more go into the electric application like electric car and other things. So this is the biggest challenge for the future power electronics engineer. So if you look at this circuit over here, you did ECE410, you know how to do this one. It's a basic circuit for diode, right? So if I look at here, the input is 120 volts, right? 170 peak. So if I do the math, do the connection over here. So if I do it, so let's do a cosine wave here. So this is 170 volts, right? That is your input. So this is your input, right? So output after diode only can conduct one way. So if I don't have the capacity, with the capacitor, let's draw the capacitor. I am saying the capacitor is big enough. So if I do the capacitor here, so you will have 170 volts clean energy at the output. This is the output, right? If I don't have the capacitor, think about it. If I don't have the capacitor, what will be the output? I'll ask you in the class for you to draw. When you don't have the capacitor, what will be the output for this one? All right. If you have a power rating, this is one of the fundamental transistor we use. That has 26 volts, sorry, 6 amps and 400 volts rating. What does it mean? That means that this one can carry 26 amp of current, all right? And it can withstand 400 volt. That means when you, like, let me draw the symbol over here. So let's say it's a transistor, right? So then it's a gate, drain, source here. So when it's on, it can carry on state it can carry 26 amp. In the off state, when it's off, state, it can have 400 volts between gate and source. So what it means, it can withstand 400 volts, it can carry 626 amps. And this rating over here, what is this rating? This rating is saying that when it's on, there is small resistance over here. It's called RDS. When it's on, when current going through that RDS is the loss. This is the loss here. So it's I squared RDS is 465 watt. That means it can handle that much losses. If you put more current through it, it's gonna burn. But if you just multiply these two items, you'll see it will be 10.4 kilowatts. So its rating is 265 watt, but it can handle 10.4 kilowatts. It's a lot bigger than your rating. So what are the application of your power electronics devices? In low voltage conversion, electronic circuits, like simple is iPhone charger or any smart design charger. There's a very small electronics, and also anything in a lower scale, right? Frequency conversion, motor control. If you do motor control, you need the frequency conversion, because your motor speed of the motor is 120 F. F is the frequency over P. P is the pole. Okay, number of poles here. Okay, all right. So that is the speed. So speed can be controlled by the frequency, where the pole is always constant. And high voltage DC conversion, and also solar. If you have a big solar application, and wind also come over here, electromechanical wind, right? And also mechatronics, any mechatronics. So these are the application you can see around the power electronics. All right. So application of high voltage DC over here, as I said, you can see the tower of power electronics. These are called SCR. These are all SCR, silicon control rectifier. This single unit can handle 1000 amps and thousands of voltage. So if you stack them, if you parallel them, you get more current. If you stack them, you get more voltage. So that's how you reach your voltage. And motor control over here, so this one can handle 100 kilowatts. And aircraft, like Boeing 787 is a more electric than ever aircraft Boeing made. So that is one of the applications in aircraft. As I said, for other applications like your iPhone charger, I mentioned before, is coming 120 volts here, and you're getting, depending on what iPhone you have, could be 3 to 5 volts, right? So look at that. This small thing is changing 120 volts to your 3 to 5 volts. And wind, as I mentioned before, solar. So those are all application of power electronics. And one of the application, small scale application, is that you have a mid-sized micro turbine, right? It can use the heat coming out of any big building, or it can be used for geological site. Those can produce around 10 kilowatts. And this basically everything is there, inverter, rectifier, everything inside that, because your incoming things variable, you have to make fixed voltage, fixed frequency. So everything inside this little box over here. And again, the future application, electric car, EV, right, is a big application now. Everyone jumping the gun to electric balls now. And data center, because we're using more and more data ever. So in the data center, you need a power electronic device to basically conditioning your data center and make sure that your data is safe. And also smaller scale now has power on chip. It's very popular now in the research scale. That's also there. And also renewable energy, all basically coming together as one application of power electronics. So what is power electronics? You have energy source over here, electric source. Then you have a power converter here. Then you have a look to load. So the power electronics basically right here is matching your electric energy source to the load. There's a goal here, and also goal that your efficiency should be 100% or close to it, and should be failure proof. And if you look at here, power electronics device basically use these three components here. Uses like a switch, it could be a transistor, MOSFET, and a capacitor and inductor. These three switches, these three thing, basic thing power converter use, and control circuit need to be needs here to control the switching. Then you can match electrical source to electrical load. And a simple application over here is an inverter. So you have a DC source over here, VDC, right? Then you're getting AC over here. So that's is basically coming through converting this source over here. So they have a 6 transistor to convert your DC to AC. And look at this symbol over here. So it's going to show you what symbol is when. Like for DC is all DC over here. This is all time varying signal over here. This is the average for the time varying signal. This is the RMS values over here, and this is also moving average, right? This is the complex phasor quantity, right? And this is small signal disturbance. So make sure that you know the symbol what used by what. And we're going to do this in the class. What is the difference? What is the relation between sinusoidal waves and RMS values? And over here, look at this here. There's a black box over here, and you're supplying 10 amps and 6 volts. On the other side, you're getting 48 volts and 1.25 amps. If you look at that, input and output power is same here. How does it happen without losses? That's the goal for power electronics. So it's something inside. So your voltage went up, right? Voltage went up. It should be must be a step up thing. So right here. So that's the thing over here. This basic thing over here. Just this basic thing over here. Making that conversion. So as I said, we have switches, like 2 switches over here. These are both are switches, diode and transistor, and an inductor and capacitor make that happen. 6 volts becomes your 48 volts. All right. And where they use them, boost converter is a big application for your space application, because space has the solar system there. So you have to take that and convert it to useful energy. There's a big research area there. And also, when you do the power conversion through the solar system, you always try to do your conversion at the max point over here. It's max energy point, right? It's called MPPT, max power point tracking. So that's the goal here. Doesn't matter how much energy you're getting from sun, you always try to do your conversion right here. So that's the maximum power point tracking. That's a very popular research in power system. And inside those energy conversion for solar system, this is the whole thing here. It has a microprocessor right here. So microprocessor make all the decision. So when how to track your maximum power point and how to also control the switching. And also it has transformer over here. It has inductor over here, and it has a capacitor there. So these are, and also all other electronic circuit. This is the regular conversion circuit for the solar system to grid. Building, you will see that there's a building out there with all solar zero carbon emission building right now, and we're gonna get to this in the second part of this lecture. So that's all for now. I'm gonna see you again for the second part of the lecture.